All right, so here's our code. Oopsie. We don't care about that. So, pen in hand. I don't have enough arms for this, right? We create our sync function, because remember, np has a sign. There's a numpy.sign. There is not, oh, good lord. There is not a numpy.sync, right? So we have to write our own sync function, which we use vectorize to do. Here is our x, right? Which is just a chunk of the real number line between -pi and pi broken into 150 samples that we're using as the input to these functions. Here is me picking a random frequency and phase, right? And then producing a sine wave of that frequency and phase, and then producing a label, category 1 for sine, doing that again for the sync function, producing a label that is a 1-hot of category 2 for sync, and then producing 600 lines with a slope from -2 to 2 and offsets from -1 to 1, right? And labeling those category 3. And if we scroll down, we see, without counting, just eyeballing it, that the data set generation is about half of this code. All right. Here I am reshaping. Why is that narrow? What the hell? Why did the line size become tiny? Are you trying to kill me, draw on screen tool? What is... Oh, gosh. Oh, that's not what I wanted to have happen either. Yeah, the draw on screen tool has decided that it wants me to die, apparently. All right, stop it. Are we good to run? Good. All right, we're just going to continue with our tiny little line. I don't know why it's tiny, right? But I've got my input. My batch dimension is none. My feature length is 1, which corresponds to that, right? I have to reshape it so it has 1 feature per sample. I have a 40 unit RNN layer. Remember that out of those 40 units, right, none of them are special memory units. Some of them the network will use for memory. Some of them it will use for output. And if I'm honest, some of them it might use for both, right? But it's got to learn to do that, especially because each of those units, right, well, yeah, neither of those units is specified for that purpose, right? It doesn't have separate memory and output. It just has hidden units, and it's got to learn to use them for one or the other. Okay. And I guess I should say, right, just like everything else, whether it uses a network for memory or output just depends on the weights, right? That's just, those weight matrices control that, right? The weights connect some inputs to some units and some outputs to some units, and those control the computation being performed. That's what controls which unit is used for what. I have my output layer, which is an ELU. Recall that, right, the RNN, because I have return sequence is false. That is the default. I could have omitted it, but I wanted to put it there so you'd know what to call that option if you needed it, right? I could have omitted that. Default is false. But because I have return sequences as false, the RNN layer, the recurrent layer, is going to consume the entire sequence and output one label only at the end, and then the dense layer and the output, right, the dense layer and output will be evaluated only once per sequence, right? The RNN layer will be evaluated length of sequence times per sequence, right? 150 times per sequence. The output layer is once per sequence. because return sequence is false. Because of all of that, right, because return sequence is false, I had to, and I apparently erased it at some point. I have to put the activation, which I accidentally erased, on this layer, right? Normally, I write the activations as a separate layer down here. But I couldn't do that this time, because if I did, the activation would only get applied once, right? It would get, because it's a separate layer after the RNN layer, it would get applied once per sequence after the RNN was completely done, and the RNN would have no activation as it passed from layer to layer to layer, from time step to time step to time step, and that would be bad. So I had to put the activation on the RNN layer, right? Like normal, I build my model, I compile, I use my tiny little learning rate, right? And then I use relatively more epochs than we've used before, right? Because when I have a tiny little learning rate, I need to train many more times. All right. So let us first off see how this does. If I actually wanted to run this for the entire 50 epochs, then obviously that would take a while. I'm just going to run it for the first couple. Oh, and we can see that I am, as usual, getting auto-grad warnings. A couple of students asked me about warnings they were seeing about end of sequence. And my answer to that is, frankly, I just kind of think that's an error somewhere in the code. I think it's just a bug in either TFDS or TensorFlow, because it does that, right? Again, I don't want to. So Google has provided us this wonderful, powerful thing for free, so I can't be too grumpy. But I think it is fair to say that their concern for code quality is perhaps not what it could be, and we just do see with just completely vanilla typical code, right? I'm not doing anything bizarre or unusual here. With just completely typical vanilla code and stock TensorFlow, we get implementation warnings, right? I didn't auto-grad anything, right? I'm just using the built-in components. One of their components is auto-gradding wrong. That's just TensorFlow, right? So when you ask me about an error you're seeing with TFDS, does that mean something has gone wrong? Probably not. It's probably an implementation warning that they didn't fix. That conversation gave me a couple of minutes of cover while we can look at how far this thing got. So we see that, again, because we are using MSE instead of categorical, that loss is fairly low, but that also might not mean anything. But we do observe that it seems to trend downward, right? Not evenly or constantly, right, and not in the last epoch, but it does tend to go down over time, and at least once it winds up kind of small, right? And we also see that the training loss is fairly consistently going down, right? So we have every reason to believe that this network is learning fairly well. Now, what is it going to look like if we see the exploding gradient problem? Well, that's really easy. I'm just going to make that bigger. So 0.05 might still seem tiny, but that's 10 times what we just had. And it might not blow up. It might. We might have to run it a couple of times to see what we get. But if we wait for a moment, we should eventually see nan, not a number. So what's happening? Model.makeTestFunction.testFunction.something. Where's the beginning of this error report? Could not transform a function. Please report this. Cause is nothing. That's excellent. To silence this warning, decorate the function with this. Although that's not in user code, right? whatever function it's talking about is not in user code that I wrote, so whoopsie doopsie. Yeah, please report it. Please report to the TensorFlow team, right? So again, I think it's fair to say, oh yeah, there's our nans, right? We got through one epoch, and then in the second epoch, our gradient exploded, right? It geometrically depended on some weight that was probably large, where large might mean greater than 1. So by the bottom, right, it's being multiplied by greater than 1 times 2,000, and it just became huge and caused a massive weight change that ultimately ended up meaning the network was radically overflowing what float 32 or float 64 could store, right? So if you see this, then a good first step is just to turn your learning rate down a lot, right? Another step might be to not use ELU, because again, that's probably more likely to cause the exploding gradient problem than tanh would be, right? So maybe go back to vanilla tanh and see if that doesn't blow up. You can actually try that, right? Let's switch that to tanh and see what we get. Our gradient will be way more likely to vanish. It should, I think, be less likely to explode. Let's find out. Oh, but yeah, right. So this is the kind of thing, I'm too lazy to report this. One reason I am too lazy to file a bug report for this is because I think it probably should already have been caught. I can understand not catching a bug if the bug only occurs in an exotic situation that is not likely to be covered by a reasonable test case. I will repeat, I didn't do anything unusual, right? I have one RNN layer, and I'm running on a Linux machine like from Conda, right? Like from pip. So using the CPU backend. So there's no reason at all that I can think of that my platform should be exotic and should have an uncommon bug. I think we just don't have, like, they don't have a test case for like the basic RNN layer for some damn reason, and I don't know why that could be. But they don't, I guess. I don't know, I could be wrong. Maybe there's something that makes my platform exotic that I don't know about. But just this, right, just like a straightforward use of the RNN layer, seems like the kind of thing that would be covered by a test case if they cared. That's my thinking. Okay, yeah, so it looks like the tanh activation does not explode, which makes a kind of sense, right? That big positive half on the ELU, okay, that large positive half, third time's the charm, that large positive half on the ELU is great for making the error signal large when you want that, right? When you're trying to overcome the vanishing gradient problem, but making your error signal large is bad if you have the exploding gradient problem, right? So tanh with its nice saturating positive half is less likely to explode, I think, right? It makes sense. So although I would probably actually want to run this many more times before I confidently said that tanh reliably wouldn't explode when ELU did. Okay. So that is our RNN overview. Let's get our slides back. Now let's break the video too.